Hello! In this video I want to explain some characteristics of electron paramagnetic resonance spectra. This is not my first video related to EPR spectra. In my previous videos I was already talking about peak doublets. Peak doublets are spectra which can be observed in solid sample containing a system of spin pairs. Here I want to talk about EPR spectra of free chemical radicals dissolved in liquids. Generally, the detailed shape of such spectra can depend on various factors, such as temperature, concentration of radicals in liquid, viscosity, solvent property, and so on. Here, I want to focus on some basic characteristics of spectra of free chemical radicals experiencing fast random translational and rotational motion in liquids. To be more clear about which system I am talking, I will give you two examples. The first example of the systems discussed here are temple radicals dissolved in water. In a standard chemical nomenclature, these radicals are called 4-hydroxy 2266 tetramethyl piperedinyl oxyl, and their structure is shown here. Another example is nitronil nitroxide radicals dissolved in benzene. The structure of these radicals is shown here. As the experiment shows, the EPR spectrum of temple radicals in liquids can roughly be described as three relatively sharp lines of equal intensity. The distance between these lines is about 15 Gauss. Okay, let us find an explanation for such spectra. First of all, I would like to point out that unpaired electrons gave rise to observed EPR spectra. In case of temple radical, this unpaired electron is localized here in the middle of an O bond. As the appearance of these three lines suggests, we have three different types of unpaired electrons in the system which give rise to these lines. Now the question is how these three different groups of unpaired electrons come into existence. The answer to this question is the hyperfine interaction of the unpaired electron with the nitrogen nuclear spin, which is equal to 1 in the case of N14. As we know, a particle with the spin 1 can have three projections: +1, 0, and -1. Hence, we can guess that the state of the nuclear spins affect the unpaired electron spins by changing its eigenfrequency, which leads to the observation of three different lines. This can be a short explanation of the temple EPR spectrum, and later we will consider it in more details. Now let us take a look on nitronil nitroxide radicals dissolved in benzene. In this case, the spectrum consists of 5 lines with different intensities. As in the previous case of temple radicals, this spectrum can be explained also by hyperfine interaction of unpaired electron spin with nitrogen nuclear spins. But here we have interaction of a delocalized unpaired electron with two nuclear nitrogen spins. A more detailed explanation of the spectra, examples of which are shown here, will be given later in this video. Okay, let us focus on the EPR spectrum of the temple radicals for the beginning. As it was already told, the spin system of the temple radical, which gives rise to the EPR spectrum, consists of unpaired electron spin and a close-by nitrogen nuclear spin. If we put these radicals into the spectrometer magnetic field B0, then the spin Hamiltonian of this system can be expressed as a sum of three terms. The first two terms correspond to unpaired electron and nitrogen nuclear spin Zeeman interaction with magnetic field B0, and the last term corresponds to the hyperfine interaction of the unpaired electron spins and nitrogen nuclear spin. The origin of the interaction between the electron spin and nitrogen nuclear spin magnetic dipoles was already discussed in this video lecture series. The link to this video is provided in the description. In this expression, S and I are electron and nuclear vector spin operators. A is a tensor which corresponds to the hyperfine interaction between unpaired electron spin and nitrogen nuclear spin. Okay, let's take a closer look on the tensor A. We will present it as a sum of two tensors. The first tensor is a unit matrix 3 by 3 multiplied by the trace of A divided by 3. And the second tensor is the rest what left from A. I will denote the first tensor as A0 and the second tensor as A bar. Obviously, the trace of A bar is equal to 0. Now I have to point out that the dissolved radicals are moving very fast due to thermal motion. It means that the tensor A is changing its value in the laboratory frame very fast. This happens because the principal axes of tensor A, which are linked to the radical molecular frame, are changing their orientation in the laboratory frame very rapidly. Here I would like to point out that the variation of the hyperfine tensor are resulting from the variation of the term A bar. The term A0 is basically a unit matrix and it does not change when we go from one coordinate frame to another. Thus, we can say that the hyperfine interaction tensor A consists of two parts. The first, A0, is a constant one, and the second, A bar, is changing very rapidly. These fast changes, which can be faster than the Larmor frequency of electron in the magnetic field B0, leads to an effective averaging of the term A bar. This allows me to simplify our Hamiltonian H. In the new expression, we have a scalar product of the vector operators I and S multiplied by a constant A0, instead of the product of the vector operator A with the tensor A and with the vector operator S. Additionally, this last term in the Hamiltonian can be simplified even further. The scalar product of the vectors I and s can be substituted just with the product of z component iz and sz. In fact, it can be shown that for high B0, the computation of the eigenstate or eigenvalues of the Hamiltonian gives almost the same result if we have this Hamiltonian with the scalar product I and S or just with the product of z component iz and sz. Now we can proceed to the computation of the eigenvalues of the Hamiltonian H using the fact that this Hamiltonian is already diagonal. Here I would like to remind you that the electron spin projection operator Sz has two eigenvectors, 1, 0 and 0, 1. The nitrogen N14 has a spin equal 1. The spin projection operator Iz has three eigenvectors, 1, 0, 0, 0, 1, 0, and 0, 0, 1. Using this information, we can construct six eigenvectors of the Hamilton operator 8 as a product of the eigenvectors of the operator Sz and eigenvectors of the operator Iz. Here they are. It can be easily proven that these six orthogonal vectors are eigenvectors of the Hamiltonian H. Using these eigenvectors, I can draw an energy diagram for this Hamiltonian, which is basically equal to the determination of the eigenvalues. I will do it step by step. I will determine which contribution to the energy gives each term in the Hamiltonian acting on each eigenvector. Okay, let's assign zero energy to this point on the diagram. Now the question is which energy will originate from the first Hamiltonian term when it acts on these three spin states with the electron spin oriented down. It can be easily shown that this action on these three states will give the same result equal to gamma E h bar B0 divided by 2, which we'll draw here below 0 because gamma E is negative for electron spin. Now let's see what do the first term of the Hamiltonian by acting on the other three states with the electron spin oriented upwards. The result will be the same for all these three states, equal to minus gamma E h bar B0 divided by 2. And we will draw it here above 0 level because gamma E is negative for electron. Now let us go to the second term corresponding to the nitrogen nuclear Zeeman spin interaction. The action of this term on these three eigenvectors with the electron spin oriented upwards will give now three different results: minus gamma NH B0 0 and gamma NH B0. They are drawn here. Similarly, the action of the second Hamiltonian term on the other three spin states is evaluated. The corresponding energy level splittings are drawn here. Now we can consider the third term in the Hamiltonian. Now the question is how this Hamiltonian term will shift the six energy levels which are depicted here. It can be easily shown that the three energy levels, which corresponds to the three states with the electron spin projection upwards, will be moved together. On the contrary, the energy levels, which corresponds to the three spin states with the electron spin projection oriented downward, will be shifted apart. Here I would like to point out that our energy diagram will have the form as depicted here if A0 is negative and absolute value of the constant A0 is much smaller than nitrogen nuclear spin-Zeeman interaction. With this we can identify three EPR transitions corresponding to three different values of nitrogen nuclear spin projection. The first corresponds to the flip of the electron spin when the nitrogen nuclear spin projection value is equal to 0. It is drawn by this green line. The second line corresponds to the electron spin flip when the nitrogen nuclear spin projection is equal to -1. This line has the lowest frequency since the distance between the energy levels is the shortest in the depicted diagram, and I will draw it with red color. The third line corresponds to the electron spin flip when the nitrogen nuclear spin projection is equal to 1. This line has the highest frequency and it is drawn with the violet color. If we put all these three lines together, we'll obtain the following spectrum, which looks quite similar as a real temple spectrum. Thus, I have made an explanation of the most important characteristics of the temple EPR spectrum. Now let us focus on the nitronil nitroxide EPR spectrum and try to explain its general features. This radical has one unpaired electron which interacts with the two nitrogen nuclear spins. Making similar steps as it was done in the case of temple, we can write the spin Hamiltonian for the nitronil nitroxide spin system. This Hamiltonian has a term corresponding to electron spin Zeeman interaction expressed via the spin operator as Z. It has a term corresponding to the nitrogen nuclear spin Zeeman interaction with the external magnetic field P0 expressed via the nuclear spin projection operator I1Z and I2Z, and it has two terms corresponding to the hyperfine interaction of the unpaired electron spin with the first nitrogen nuclear spin and with the second nitrogen nuclear spin. Here I have to point out that similarly as in the case of temple radicals, the hyperfine interaction is described by a reduced expression containing only the products of SZ and IZ projection operators. In general, the hyperfine interaction is described by a full product of vector spin operators I and S with the hyperfine interaction tensor. As explained above, such simplification is possible in the case of fast rotating motion of radicals in liquids. Okay, Let us now determine the eigenvalues of this Hamiltonian. I will start by reminding you the eigenvalue and eigenvectors of the operator as z, and also the eigenvalue and eigenvectors of the operators I1z and I2z. Okay, the electron spin projection operator as z has an eigenvalue 1/2 with the corresponding eigenvectors 1, 0, which is usually denoted as ket 1/2. It also has an eigenvalue -1/2 with the corresponding eigenvectors 0, 1, which is usually denoted as ket -1/2. The nitrogen isotope N14 has spin 1. The spin projection operator Iz has three eigenvalues, 1, 0, and -1, with the corresponding eigenstates, which can be denoted via ket vectors. Since nitronil nitroxide has two nitrogen nuclei, I have to write the same eigenvalues and eigenstates for the second nitrogen nucleus. Here I have to say that the spin states of both nitrogen nuclei are the same only in some special sense when they are considered as the building blocks of a more general quantum state of the whole radical spin system. In this general state, they will be distinguished by the places where they enter the general product state of the whole radical spin system. Okay, let us construct such a general product spin state, with the electronic spin state ket S in the first position, with the nuclear spin state ket I1 for the first nitrogen nucleus in the second position, and with the nuclear spin state ket I2 for the second nitrogen nuclear spin in the third position. It can be easily shown that such product states are eigenvectors of our spin Hamiltonian. With this, we can calculate the energy level of our spin system by calculating the standard bracketing of the operator H with our spin state characterized by three quantum magnetic numbers S, I1, and I2. This gives us a result consisting of three terms. The first term corresponds to the electron-spin Zeeman interaction and depends on the spin quantum number S, which can be +1/2 or -1/2. The second term corresponds to the nitrogen nuclear spin Zeeman interaction and depends on the sum of the magnetic quantum number I1 and I2, which each can be +1, 0, or -1. And the third term corresponds to the hyperfine interaction of the unpaired electron spin with the both nitrogen nuclear spins, and it depends on the product of S and the sum of I1 and I2. These expressions allows us to draw an energy diagram for all 18 quantum spin states which we obtain here. The number 18 is obtained as the number of all possible combinations of the two electron spin state, of the three nuclear spin state, of the first nitrogen, and of the three nuclear spin state of the second nitrogen nucleus. I will draw this diagram step by step, or better to say, term by term, as it was done in the case of Temple. First of all, I will draw the contribution to the energy from the first term for the two possible values of S equal to plus 1/2 and minus 1/2. As we see, this term does not depend on the magnetic quantum number I1 and I2, and it will be the same for all possible 9 combinations of I1 and I2. Now let us add the contributions from the second term to the obtained two levels. The second term does depend on the I1 and I2. Since both I1 and I2 can have three different values minus 1, 0, 1, there are in total 9 combinations of I1 and I2. However, they give only 5 different results when summed up. The largest value of the sum I1 plus I2 is equal to 2, and it is obtained in the case when both I1 and I2 are equal to 1. The second largest value of the sum I1 plus I2 is equal to 1. However, it can be realized in two different ways. The first is when the I1 is equal to 1 and I2 is equal to 0, and the second possibility is when the I1 is equal to 0 and I2 equal to 1. The third largest value of the sum I1 plus I2 is equal to 0. In this case, this value can be already realized in three different ways. The first possibility is when I1 and I2 are both equal to 0. The second possibility is when I1 is plus 1 and I2 is minus 1. And the last possibility is when the I1 is equal to minus 1 and I2 is equal to 1. So we can go on and determine the other two possible values of the sum I1 plus I2 and their populations. With this, we can determine the value of the second term in the expression for energy for all 9 possible nuclear spin states. The result of these calculations are drawn here in the diagram. Now we have arrived at the last term corresponding to the hyperfine interaction. The behavior of this term is in some sense similar to the behavior of the second term. However, it depends additionally on the magnetic quantum number S. This will have the opposite effect on the spin state with S equal 1/2 and S equal minus 1/2. In the case of S equal minus 1/2, the 5 belonging energy levels will be moved together, and in the case of S equal 1/2, the 5 corresponding energy level will be moved apart. Now we can identify 5 transitions where the electron spin flips but the value of I1 and I2 is preserved. The first transition with the lowest frequency, which I will draw with the red color, occurs between the states which have I1 plus I2 equal to 2. The second transition between the state with I1 plus I2 equal to 1 is drawn with the orange color. The central transition with I1 plus I2 equal to 0 is drawn with the green color. The fourth line with the I1 plus I2 equal to minus 1 is drawn with the blue color. And the last line corresponding to the I plus 2 equal to minus 2 is drawn with the violet color. Now we can put all these 5 lines together into one spectrum as if it would be measured in a frequency scan experiment. Here we have got 5 lines with 3 different intensities. The intensity of the first and of the fifth lines are equal, and we will use their magnitude as a unit. The intensity of the second and the fourth lines are also equal, and their magnitude is equal to 2 in our case. The magnitude of the central line is equal to 3. Such difference in the line magnitudes can be explained by the population of the energy levels. For example, the central line is created by 3 quantum spin states with I1 and I2 equal to 0, with I1 equal to 1 and I2 equal to minus 1, and with I1 equal to minus 1 and I2 equal to plus 1. Therefore, it has a magnitude equal to 3. Generally, the difference in the line magnitudes is attributed to the interaction of the electron spin with the equal nuclear spins. For comparison, in the case of temple radical, we had interaction of the electron spin with one nitrogen nuclear spin, and it gave us 3 equal lines. If we had more spins in our spin system, we can use the same procedure as described here to explain the major characteristics of its EPR spectrum. With this, I would like to finish and invite you to listen to other lecture from my channel. Thank you for watching this video.